Welcome, curious minds, to the deep dive. Today, we're plunging headfirst into, well, one of the most profound cosmic mysteries out there. It's something that really reshapes how you think about reality. Just imagine for a second that everything you've ever seen, ever perceived, every star, every galaxy, even, your own body, all of that makes up just a tiny, tiny fraction, like 5% of what's actually out there. So what about the other 95%? Well, it's completely dark, it's mysterious, and we fundamentally don't know what it is. It's like discovering you've lived your whole life in a house, only ever seeing the furniture right, and then finding out the walls, the foundation, even the air itself are made of something totally alien, something you just can't see or touch, something that actually bends light and reshapes space. That's the staggering 95% unknown we're diving into today. So our mission here is to try and cut through some of that complexity surrounding dark matter and dark energy. We want to pull out the really important nuggets of knowledge from, the latest science. And look, this isn't just about abstract physics, although, yeah, there's plenty of that.
It's really about understanding the very fabric of our universe, what holds it together, what's pushing it apart, and maybe even what its ultimate fate might be. These two things, dark matter and dark energy, they're the most dominant forces in the cosmos, but also the most enigmatic. Okay, let's really try and unpack this.
And that scale you mentioned, it's genuinely humbling when you stop and think about it. Everything we can see, everything we interact with, stars, planets, galaxies, us, the atoms in your hand, it's only 5% of the total mass and energy in the universe.
Just 5%. It's wild.
It really is. So that means 95% is made up of these two, mysterious entities, dark matter and dark energy. And they're not just some theoretical ideas floating around. They seem to be the hidden architects. They're absolutely fundamental to how galaxies even formed in the first place, how the whole universe behaves on the biggest scales, and what its ultimate destiny might be. Maybe just to start, a quick distinction between the two might help set the stage. You can think of dark matter as a kind of cosmic cement. It's like an invisible gravitational glue that pulls things together, helps bind structures like galaxies. It's the attractive force.
Okay, so it pulls things together.
Right. Then dark energy, that's the opposite. It's the repulsive force. It acts almost like a pervasive anti-gravity, pushing everything apart.
Yeah.
It's actually driving the universe's expansion, making it speed up, accelerate.
So one pulls, one pushes. Like a cosmic tug of war.
Exactly, a cosmic tug of war. And our entire visible universe is basically caught in the middle of this epic struggle between these two unseen giants. Its fate kind of hangs in the balance.
And when you look at that cosmic census, those proportions are just, astonishing. Current estimates are roughly 68% dark energy?
About that, yeah.
And 27% dark matter, which leaves that tiny, almost afterthought 5% for everything else, all the normal stuff.
Stars, gas, dust, planets, us. Yep, 5%. The hidden majority is a good way to put it.
But here's where it gets really interesting for me. What does dark actually mean here? Because it's not just like, a dark room where you can't see.
Right, that's a crucial point.
It means something more fundamental, doesn't it?
Yeah, it does. Dark here means these things don't interact with light, or any other form of electromagnetic radiation for that matter.
So they don't reflect light, they don't absorb it, they don't emit it.
Exactly, they're truly invisible, transparent. They're passing through us, through the Earth, through the sun, right now, and we don't feel a thing.
And this is the key to how we even know they exist, right?
Yeah.
They do interact with gravity.
That's the key, absolutely.
Their gravitational pull, while maybe subtle nearby, becomes enormous on cosmic scales.
Precisely. And that's how we infer they're there. We see their gravitational effects on the things we can see, like stars and galaxies.
It's kind of like feeling the wind, maybe?
Yeah.
You can't see the air itself, but you see the trees moving, you feel it on your skin.
That's a great analogy, yeah. We see the effects even if we can't see the cause directly. So let's dig into those definitions a bit more, because their roles are so distinct. Dark matter, like we said, is the attractive force, that cosmic cement. Its main job, as far as we know, is exerting gravity. It pulls matter together, but it doesn't interact with light. So without it, the gravity from just the visible stuff, the stars and gas, it just wouldn't be enough.
Not enough to hold galaxies together while they're spinning so fast.
Exactly, or galaxy clusters. They just fly apart. Dark matter provides that extra invisible gravitational scaffolding needed to hold them together. Dark energy, though, is the repulsive force. It's different. Think of it more like a strange pressure or energy density inherent in space itself, and it's actively driving the universe's expansion, making it accelerate, pushing galaxies further and further apart, faster and faster.
So dark matter tries to build structures, dark energy tries to blow them apart.
That's the dynamic. Yeah. And, this immediately raises a really important question.
Which is,
How do we know? How do we know all this invisible stuff is really out there if we can't see it, can't touch it, can't, put it in a lab?
right, where's the proof?
And that's where the evidence comes in. It's a fascinating story built up over decades, and you really see their combined effect on the largest scales. They're literally sculpting the universe's architecture. When we run simulations or look at galaxy surveys, the universe isn't uniform. It has this incredible clumped and web-like structure.
Cosmic web, yeah.
Exactly. These vast thread-like filaments made of galaxies and dark matter stretching across millions, even billions of light years. These filaments connect at dense nodes, forming galaxy clusters. And in between are these enormous, almost empty regions called voids, like giant cosmic bubbles.
And this whole structure depends on dark matter and dark energy.
Fundamentally, dark matter provides the gravitational seeds for the structures to form along these filaments, and dark energy influences how quickly those structures grow and at how far apart they end up. Without them, the universe would likely just be a smooth, featureless soup of gas.
It's incredible. These invisible forces dictating the whole cosmic landscape. And the first inkling that something unseen was shaping things came, well, quite a while ago, didn't it? Some really puzzling observations.
Yeah, the detective story starts way back.
We're talking the 1930s, right? With Fritz Zwicky.
That's right. Fritz Zwicky, a Swiss astronomer, quite a character apparently. He was studying the Coma cluster.
Which is this huge group of galaxies.
Massive collection, yeah, about 1,000 galaxies all swirling around. And Zwicky was measuring how fast they were moving within the cluster.
And he found something weird?
Very weird. He calculated the speeds, and they were just zipping around way too fast.
Yeah.
Based on the gravity from all the stars and gas he could see in those galaxies. Well, there wasn't nearly enough gravity to hold the cluster together.
They should have just flown off, like horses flying off a carousel spun too fast.
Exactly like that. The cluster should have dispersed. But it wasn't. It was clearly gravitationally bound.
So Zwicky had an idea.
He did. He boldly proposed there must be some kind of unseen matter, something invisible providing the extra gravity. He called it dunkel materie, dark matter. And his calculations suggested there had to be a lot of it. Maybe 400 times more mass than what was visible.
Wow, that must have sounded crazy back then.
Oh, it did. It was a pretty radical idea, and it wasn't widely accepted for a long time. People were skeptical.
But then, decades later, in the 70s, the idea got a huge boost from Vera Rubin and Kent Ford.
Yes, their work was absolutely pivotal. They weren't looking at clusters, but at individual spiral galaxies like our own Milky Way.
And they were looking at how things rotate within those galaxies.
Precisely. They were measuring the speeds of stars orbiting the galactic center. Now, normally you'd expect things further out to orbit slower, right? Like planets in our solar system, Mercury zips around, Neptune crawls, Kepler's laws.
Makes sense. Gravity gets weaker further out.
Right. But that's not what Rubin and Ford found. They discovered that stars on the outer edges of these spiral galaxies were orbiting just as fast, sometimes even faster, than stars closer to the center.
Whoa. So the orbits were flat, not dropping off.
Exactly. Flat rotation curves. It was a huge puzzle. It completely contradicted what you'd expect based on the visible matter alone.
Which strongly suggested more invisible stuff.
It strongly suggested there had to be a massive, extended halo of invisible matter surrounding these galaxies, something providing the extra gravitational pull needed to keep those outer stars orbiting so quickly.
A dark matter halo.
Yep. And Vera Rubin, who is a real pioneer, she put it very clearly. There has to be a lot of mass to make the stars orbit so rapidly, but we can't see it. We call this invisible mass dark matter.
So Zwicky's funny observation in clusters and Rubin and Ford's in individual galaxies, they were pointing to the same thing.
They really were. These weren't just minor anomalies. They were fundamental discrepancies that demanded an explanation. And dark matter became the most compelling one. It laid the groundwork for decades of research. And that's exactly why visible matter alone just doesn't cut it. Like you said, without dark matter, galaxies wouldn't look the way they do, clusters wouldn't hold together. The gravity from stars and gas is simply insufficient.
So those early clues were the start, but the case has gotten stronger since then.
Oh, much stronger. Modern cosmology has built up multiple independent lines of evidence that all point towards dark matter being real and abundant. It's become a cornerstone of our understanding. One of the most powerful pieces of modern evidence is something called gravitational lensing.
Okay, lensing, like
Yeah.
a lens bends light.
Exactly. But in this case, the lens isn't glass, it's gravity itself. Einstein's theory tells us that mass warps space-time, and light follows those warps. So dark matter, because it has mass, creates a gravitational field that can bend the light from distant galaxies as that light travels towards us through space.
So the dark matter acts like a giant, invisible magnifying glass, or maybe a funhouse mirror.
That's a good way to think about it. It distorts the images of the background galaxies. We might see them stretched into arcs, or even see multiple images of the same galaxy.
Like ripples in a pond, you said earlier. We see the effect on the light, even if we can't see the rock, the dark matter that caused it.
Precisely. And by carefully mapping how the light from thousands of distant galaxies is distorted, we can actually reconstruct where the invisible mass, the dark matter, must be located and how much of it there is. It's an incredibly powerful tool, and the absolute classic example, the one often called the smoking gun evidence, is the bullet cluster.
Right, you mentioned that. It's two galaxy clusters colliding.
Caught right in the act of merging, yeah. It's a spectacular cosmic collision. Now, what's really cool is how different components behave during this smash-up. There's the hot gas between the galaxies that's normal, visible matter. When the clusters collided, this gas slammed into itself, slowed down due to friction and pressure, and created a huge shockwave. We can see this hot gas piled up near the center of the collision using X-ray telescopes.
Okay, so the normal gas got stuck in the middle.
Right. But then astronomers used gravitational lensing to map where most of the mass in the system actually is. And they found that the bulk of the mass wasn't where the hot gas was. Instead, the mass peaks were located out with the galaxies themselves, having passed right through the collision almost completely unaffected.
So the galaxies and the dark matter just sailed through while the gas got held up.
Exactly. This physical separation is incredibly powerful. It shows that most of the mass in the clusters isn't the hot gas, it's something else, something that doesn't interact except through gravity. That something else is dark matter. It passed through like ghosts while the normal matter interacted strongly. And it's not just the bullet cluster. We see similar things in other colliding clusters, and detailed mapping of dark matter using lensing in clusters like Abel 1689 shows these vast, clumpy distributions consistently. Plus, if you look at the cosmic microwave background, that baby picture of the universe.
The afterglow of the Big Bang.
Right. The tiny temperature fluctuations, the sort of lumpiness in that ancient light, carry information about what the universe was made of back then. And the specific pattern of those fluctuations can only be explained if dark matter made up a significant chunk, about 27% of the universe's energy density very early on. It acted as the gravitational seeds that allowed the first structures, the precursors to galaxies, to start forming.
Wow, so it's woven into the very fabric of the early universe, too.
Absolutely. It's so fundamental now that it's a crucial part of the standard model of cosmology. That's our best framework for understanding the universe's birth and evolution. You simply can't build a model that matches our observations without including dark matter. Without it, frankly, we can't explain how galaxies formed, how the cosmic web arose, how we got here.
Okay, so the evidence seems overwhelming. Dark matter's out there, it's shaping everything. The next massive question is, what is it? What is this stuff actually made of?
Right. The billion-dollar question.
It's probably easier to start with what it's not, yeah. Eliminate some possibilities.
That's usually how scientists approach it, yeah. Rule things out.
So first off, it's not just like regular stuff that's dark, like clouds of gas or dead stars.
Right. It's definitely not ordinary baryonic matter. That's the stuff made of protons and neutrons, like us, planets, stars. We call dark matter non-baryonic.
But how do we know that?
Well, a few reasons. If it were just huge clouds of normal matter, even if cold and dark, they would still absorb or block certain wavelengths of light passing through them. We'd see their signatures in the spectra of distant objects. We don't.
Okay.
Also, those precise measurements of the cosmic microwave background, and also calculations based on the abundance of light elements like hydrogen and helium created in the Big Bang, something called Big Bang nucleosynthesis, they both very tightly constrain the total amount of baryonic matter the universe can possibly contain. And it only adds up to about 5%. There just isn't enough normal matter out there, hidden or otherwise, to account for the 27% needed for dark matter.
Okay, so not normal matter in disguise. What about antimatter? Could it be that?
Good thought, but probably not. Antimatter annihilates spectacularly when it meets regular matter, producing very specific high-energy gamma rays. If dark matter halos were made of antimatter, we'd expect to see a constant glow of these gamma rays from all directions as stray particles of normal matter run into the halo. We don't observe that widespread annihilation signal.
All right, so not antimatter. What about black holes? They're massive and dark.
Black holes definitely exist, and they contribute some mass, but probably not the bulk of dark matter, especially not huge, galaxy-sized primordial black holes. If dark matter was mostly made of such large objects, we'd expect to see very specific, strong gravitational lensing effects, like multiple distinct images of background stars, much more often than we do. The lensing we see is generally smoother, more diffuse, suggesting the mass is spread out more evenly, not concentrated in massive black holes.
Okay. And one more thing often mentioned, machos, massive compact halo objects.
Right, machos. That was a popular idea for a while. These would be things like brown dwarfs, failed stars, neutron stars, or smaller stellar mass black holes, things made of normal baryonic matter, but just very faint or dark, lurking in galactic halos.
So regular stuff, just hard to see.
Exactly. And people did extensive searches for them using a technique called microlensing. They monitored millions of stars, looking for brief, temporary brightenings caused by a macho passing in front of a background star and focusing its light.
Did they find any?
They found some microlensing events confirming machos exist, but nowhere near enough to account for all the dark matter needed, far too few. And critically, remember, machos are baryonic. They're made of protons and neutrons, and we already know from the CMB and Big Bang nucleosynthesis that dark matter has to be non-baryonic. So machos are out as the primary component.
So dark matter has to be something else,
Yeah.
something entirely new.
Something exotic, yeah. Likely a new type of fundamental particle, not part of the standard model of particle physics that describes the forces in particles we know. Which brings us to the candidates. If it's not any of that stuff, what could it be? The leading idea for decades has been WIMPs.
WIMPs, weakly interacting massive particles.
Exactly. The name tells you the key properties. Weakly interacting means they barely interact with normal matter or light, hence why they're dark and hard to detect. They mostly just feel gravity. Massive means they have enough mass to provide the gravitational effects we see. And particles means they're some kind of subatomic particle.
But not protons or neutrons. Non-baryonic.
Correct. A fundamentally new kind of particle. Now, what specific particles could be WIMPs? Well, neutrinos were an early thought. We know they exist, they're weakly interacting, they have a tiny bit of mass.
But not enough mass.
Not nearly enough, and also they move too fast. They're what's called hot dark matter. Because they're so light and relativistic, they tend to smooth out structures rather than helping them clump together gravitationally. So neutrinos contribute a tiny fraction, but they can't be the main dark matter component that formed galaxies.
Okay, so not neutrinos. What else?
More exotic theoretical particles are better candidates. One is the axion. It's a hypothetical particle proposed to solve a completely different problem in particle physics related to neutron properties. Axions would be incredibly light, but potentially very numerous, and they interact very weakly. They're a possibility.
And the other big one, neutralinos.
Neutralinos, yes. These come from a theory called supersymmetry, or CSY, which is an extension of a standard model. CSY predicts that every known particle has a heavier superpartner. The neutralino would be the lightest stable superpartner, and it naturally has the properties of a WIMP, stable, massive, and weakly interacting. It was considered the prime candidate for a long time.
But the key word is theoretical.
Absolutely. Axions, neutralinos, other WIMP candidates, none of them have been directly detected yet, despite many sophisticated experiments trying to find them. That's a major ongoing challenge. So whatever it is, this dark matter stuff isn't just floating around randomly. It's believed to form these huge, diffuse, roughly spherical halos around galaxies.
Extending way beyond the visible stars.
Oh yeah, maybe 10 times further out than the luminous disk you see in pictures. This halo contains most of the galaxy's mass and provides the gravitational backbone.
And galaxy clusters have even bigger halos.
Enormous ones, yes. The dark matter in a galaxy cluster typically outweighs all the visible matter, all the stars and gas in hundreds or thousands of galaxies, by a factor of 5 or more. It's the dominant gravitational component holding the whole cluster together and influencing how the galaxies move within it. It truly is the invisible scaffold of the cosmos.
Okay, that gives us a pretty solid picture of dark matter. The invisible glue, the scaffolding. But then there's the other 68% of the universe, dark energy, the accelerating push. And this is maybe even weirder.
It's certainly a profound mystery, and its discovery really turned cosmology on its head.
Because for a long time, we knew the universe was expanding, right? That goes back to Hubble in the 1920s.
Right. Edwin Hubble showed galaxies are moving away from us, and the farther away they are, the faster they recede. That was the foundation of the Big Bang theory. Everything started close together and has been expanding ever since.
But the assumption was that gravity should be slowing that expansion down, wasn't it? Like throwing a ball up in the air, it slows down, maybe stops, maybe falls back down.
Yeah.
Exactly. Everyone expected the expansion to be decelerating due to the mutual gravitational pull of all the matter in the universe. The big question was whether there was enough gravity to eventually stop the expansion and cause a big crunch, or if it would expand forever, but more and more slowly.
But then, the late 90s happened, and something completely unexpected.
Completely unexpected, a genuine shock to the system.
It came from studying supernovae,
Yes.
specifically type Ia supernovae.
Yes, 2 independent teams of astronomers were using type Ia supernovae as standard candles.
Standard candles,
Yeah.
meaning they always have the same brightness.
Pretty much. These specific supernovae occur when a white dwarf star in a binary system steals matter from its companion, reaches a critical mass limit, the Chandrasekhar limit, and explodes. Because they all explode at roughly the same mass, they have remarkably consistent peak luminosity. They're incredibly bright, visible across billions of light years.
So you can measure how far away they are by how bright they appear. Fainter means further away.
Exactly. And you can also measure their redshift, which tells you how fast they're moving away from us due to the universe's expansion. So by comparing distance from brightness and speed from redshift for supernovae at various distances, you can map out the expansion history of the universe, look back in time.
And what did these teams find when they looked at the really distant supernovae?
They found something stunning. The most distant supernovae were consistently fainter than expected for their redshift.
Fainter, meaning they were further away than they should have been if the expansion was slowing down.
Precisely. The only way to explain why they were so unexpectedly far away was if the expansion of the universe hadn't been slowing down at all. In fact, sometime in the last few billion years, it started speeding up, accelerating.
Wow, so the universe is pushing itself apart faster and faster.
That was the conclusion. And it was radical. I remember reading about Brian Schmidt, one of the team leaders, describing his reaction as somewhere between amazement and horror.
Horror. Why horror?
Well, amazement at the discovery, but horror because it seemed to contradict everything they thought they knew. It implied some strange, unknown energy was dominating the universe and pushing it apart. It was a complete paradigm shift. And what's really interesting here is, unlike dark matter, where there are still some debates about its exact nature, the evidence for this accelerated expansion, and thus for dark energy, has become incredibly solid since then.
So more observations have confirmed it.
Many more. From different types of observations too, studies of the cosmic microwave background, large-scale galaxy clustering patterns, they all independently point to the same conclusion. The universe's expansion is accelerating, driven by something we call dark energy. Even scientists who were initially skeptical have largely come around because the observational data is just so compelling. Now, knowing that it's happening is one thing. Knowing what dark energy actually is, that's a whole different ballgame. It's arguably the biggest mystery in physics today.
But there are ideas, right? Theories.
Oh, yes. And interestingly, the leading idea actually ties back to Einstein, even though he didn't know about dark energy.
His biggest blunder. The cosmological constant.
That's the one. Einstein added this term, lambda, to his equations of general relativity because he thought the universe should be static. The constant represented a kind of energy inherent in empty space itself, which would counteract gravity's pull and keep the universe from collapsing.
But then Hubble found the universe was expanding, so Einstein ditched the constant.
He did. He called it his biggest blunder. But ironically now, a cosmological constant, this idea that empty space itself possesses a fundamental energy density, is the simplest and leading explanation for dark energy. The really weird property of this vacuum energy, if that's what it is that its density stays constant even as the universe expands.
Wait, how did that work? If space gets bigger, shouldn't the energy get diluted?
You think so, like matter does. But with vacuum energy, as space expands, you just get more space. And each new bit of space comes with its own chunk of vacuum energy. So the energy density, the amount of energy per unit volume, remains constant.
And that constant energy density creates a repulsive force.
According to general relativity, yes. A constant positive vacuum energy creates a negative pressure, which acts like anti-gravity, pushing space apart and driving accelerated expansion. It fits the observations remarkably well.
But we don't know why space would have this energy, or why it has the specific value it seems to have.
Exactly. That's the huge mystery. Why does this cosmological constant exist, and why is its value so incredibly small compared to what particle physics theories might predict? Which leads to other ideas. Maybe dark energy isn't a constant.
Like it changes over time.
Possibly. One alternative comes from quantum physics. Quantum field theory suggests that even empty space isn't truly empty. It's fizzing with virtual particles constantly popping in and out of existence. This activity should give space a vacuum energy.
Okay, sounds promising.
Well, yes and no. When physicists tried to calculate how much energy this quantum vacuum should have based on known particles and forces, the number they got was absurdly, catastrophically enormous.
How enormous?
Something like 10 to the power of 120 times larger than the value we actually observe for dark energy.
10 with 120 zeros after. That's not even close.
Not even remotely close. It's been called the worst theoretical prediction in the history of physics. It's a massive discrepancy and known as the cosmological constant problem, and it tells us we're missing something really fundamental in our understanding of gravity and quantum mechanics. So another possibility is that dark energy isn't constant vacuum energy, but rather something dynamic, something that can change over time and space. This is often called quintessence.
Quintessence, like a fifth element.
Sort of, yeah. It's proposed as a new kind of energy field or fluid that permeates the universe. Unlike a cosmological constant, its energy density could evolve as the universe expands. Maybe it was less important in the past and only started dominating recently, causing the acceleration.
But we don't know what this field would be made of either.
No, its nature is entirely hypothetical at this point. It's another placeholder for something we don't understand, but it offers more flexibility than a simple constant. And then there's a more radical idea. Maybe there is no dark energy.
Wait, but the acceleration is real.
The acceleration seems real, but maybe it's not caused by a new energy source. Maybe it's a sign that Einstein's theory of gravity, general relativity, is incomplete.
So we need to modify gravity itself.
That's the suggestion. Perhaps gravity behaves differently on very large cosmic scales than it does in our solar system or within galaxies. Maybe there are subtle modifications to gravity that naturally cause acceleration without needing any extra dark component.
That feels like a pretty big step, messing with Einstein.
It is. General relativity has passed every test thrown at it so far on smaller scales. But the universe is throwing us a curveball with acceleration. So some physicists are exploring these modified gravity theories. It really raises that fundamental question. Do we need new stuff, dark energy, or do we need new rules, modified gravity?
And figuring that out needs more data.
Lots more data. More precise measurements of the expansion history, the growth of structures, gravitational lensing. Comparing observations to the predictions of these different models is how we'll hopefully figure out which path is right. But whatever its ultimate nature, cosmological constant, quintessence, modified gravity, the effect is clear. This dark energy is driving the accelerated expansion. And because it dominates the universe's energy budget now, it's the key factor determining the ultimate fate of the cosmos.
Whether it ends in a big freeze or a big rip.
Exactly. If dark energy stays constant or grows stronger, the expansion will continue accelerating, leading eventually to a cold, dark, empty, big freeze, where galaxies are isolated and stars burn out. Or potentially, if it gets really strong, a big rip, where the expansion becomes so violent it overcomes gravity, tearing apart galaxies, stars, planets, and maybe even atoms themselves. The nature of dark energy holds the key to the universe's very end state.
So putting it all together, what does this all mean? We've got dark matter pulling things together, dark energy pushing them apart. They're both dark, both dominate the universe, but they're completely different beasts.
Fundamentally different, yeah. Despite the similar names, they have almost opposite effects.
That tug-of-war analogy seems pretty spot on. One's the cosmic glue, the other's the cosmic accelerator pedal stuck to the floor.
That's a great way to put it, yeah. The entire evolution and fate of the universe hinges on the interplay between these two dominant, mysterious components. Maybe we can just quickly recap the key differences side by side to make it super clear.
Good idea. Let's break it down.
Okay, first, composition.
Yeah.
What are they made of? Dark matter. We think it's some kind of new, exotic, non-baryonic particle like WIMPs or axions, something beyond our current standard model.
Right. And dark energy.
Dark energy seems to be some form of energy, not particles in the same way. Maybe it's the energy of empty space itself, cosmological constant, or maybe some unknown dynamic field, quintessence, totally different physical nature. Next, abundance. How much is there? Dark energy is the clear winner, about 68% of the universe's total mass energy.
With dark matter at a hefty 27%.
Right, leaving just that 5% for us and everything we see. Then, distribution. Where is it? Dark matter clumps together. It forms those halos around galaxies and clusters, tracing the cosmic web structure. It's concentrated where normal matter is because gravity pulls it there.
But dark energy is smooth.
Apparently, yes. It seems to be spread out uniformly throughout all of space, like an inherent property of the vacuum itself. It doesn't clump up gravitationally. Okay, gravitational effect. This is the big contrast. Dark matter is attractive, it pulls things together, helps form structures, acts like glue.
And dark energy is repulsive. It pushes things apart, drives accelerated expansion, acts like anti-gravity on large scales.
Perfect summary. Diametrically opposed effects. And how do we know they exist? Their signatures or evidence. For dark matter, it's all about its gravitational influence on things we can see. Those flat galaxy rotation curves, gravitational lensing distorting light from distant objects like in the bullet cluster, and its imprint on the cosmic microwave background fluctuations.
Indirect evidence through gravity.
Exactly. For dark energy, the primary evidence is that observed accelerated expansion of the universe, measured using type Ia supernovae as standard candles. But it's also confirmed by detailed studies of the CMB and the large-scale distribution of galaxies, like those baryon acoustic oscillations, or BAO.
Right, those giant cosmic rulers. So, evidence for acceleration itself.
Correct. Finally, their overall impact on the universe. Dark matter was crucial early on. It provided the gravitational seeds needed for galaxies and the cosmic web to form in the first place. It holds those structures together today.
The architect.
Sort of, yeah. While dark energy is all about the future. It dictates the late-time evolution of the universe, driving the accelerated expansion and determining its ultimate fate, big freeze, big rip, or something else.
Engine driving the endgame.
That's a good way to think about it. So, yeah, two totally different roles, two totally different mysteries, both fundamental to understanding our cosmos.
And tackling these twin mysteries, figuring out what this 95% actually is, it's just...
Well, it's one of the absolute biggest challenges in science today, right?
Right.
Astrophysics, cosmology, particle physics, they're all converging on this.
It's a massive undertaking, truly one of the frontiers of human knowledge.
What's fascinating, though, is how scientists are trying to crack it. It's not just one approach, it's this incredible multi-pronged attack. Absolutely. It requires pushing technology to its limits, combining observations of the largest scales with experiments searching for the tiniest particles, and using incredible computational power to put it all together. It's a global scientific effort. And fundamentally, like you said earlier, it all comes down to getting more and better data. We need incredibly precise measurements from a whole range of sources. So on the observational side, looking up at the sky, we have amazing tools. Space telescopes like Hubble, which still delivers incredible science. The James Webb Space Telescope, which is peering deeper into the infrared universe than ever before, seeing the very first galaxies forming.
Which tells us about early structure formation, tied to dark matter.
Exactly. And then there's the upcoming Nancy Grace Roman Space Telescope. It's designed specifically for wide field surveys, mapping huge areas of the sky to study both dark energy via expansion history and dark matter via gravitational lensing with unprecedented precision. And complementing those are the ground-based giants, telescopes like the South Pole Telescope looking at the CMB in incredible detail, instruments like DSI, the Dark Energy Spectroscopic Instrument in Arizona.
What's DSI doing?
DSI is creating a massive 3D map of the universe by measuring the distances and positions of tens of millions of galaxies and quasars. This map traces the cosmic web and those BAO features, allowing scientists to precisely measure the expansion history and the growth of structure over cosmic time, testing dark energy models.
Wow.
Then there's the Dark Energy Survey, DES, which already finished its observations but provided a ton of data on lensing and galaxy clustering. And the big one coming online soon is the Vera C. Rubin Observatory in Chile.
Named after Vera Rubin.
Fittingly, yes. Its Legacy Survey of Space and Time, LSST, will survey the entire southern sky repeatedly for 10 years, creating this incredible time-lapse movie of the cosmos. It will find billions of galaxies, track supernovae, map dark matter through lensing, just an immense flood of data to tackle these questions.
So the goal of all these sky surveys is basically to map where stuff is and how it's moving over billions of years of cosmic time.
That's the core idea. By mapping the distribution of dark matter and precisely measuring the effects of dark energy on expansion and structure growth, we constrain the possibilities for what they could be. And an interesting side note on the surveys relates to those dwarf galaxies you hear about.
The really small, faint ones orbiting bigger galaxies like ours.
Yeah. Our standard models of dark matter, particularly WIMP-based models, predict that large dark matter halos should contain hundreds, maybe thousands, of smaller subhalos which should host these dwarf galaxies. But we observe fewer than predicted, the missing satellites problem.
So finding more, or not finding more, tests the dark matter models.
Exactly. These deep surveys, like Rubin's LSST, are crucial for finding these faint dwarfs and testing whether our models of cold dark matter hold up on these smaller scales, or if maybe dark matter has slightly different properties. Okay, so that's looking up. But scientists are also looking down, trying to catch dark matter particles right here on Earth.
The direct detection experiments.
Right. Building these incredibly sensitive detectors, usually deep underground, to shield them from cosmic rays and background radiation.
Why underground?
To get away from all the other particles constantly bombarding the Earth's surface. You need an ultra-quiet environment to have any hope of detecting the incredibly rare, incredibly faint signal of a WIMP bumping into an atomic nucleus inside your detector.
Like finding a whisper in a hurricane.
Pretty much. Experiments like LUX Zeppelin, LZ, in South Dakota, Xenon in Italy, Pandax in China, they use large tanks of noble liquids like xenon or argon, waiting patiently for that tiny flash of light or charge that signals a WIMP interaction. So far, no definitive signal, but they're getting more and more sensitive. And another angle is particle accelerators, like the Large Hadron Collider, LHC, at CERN.
Can they make dark matter?
That's the hope. By smashing protons together at extremely high energies, the LHC creates showers of known particles. But physicists look for anomalies. Maybe they could produce WIMPs or other dark matter candidates directly. Or perhaps more likely, they might see signs of dark matter indirectly. If dark matter particles are produced in a collision but escape the detector without interacting because they're weakly interacting, they would carry away energy and momentum. So physicists look for events with missing energy, where the energy of the particles they do see doesn't add up, suggesting something invisible carried some away. That could be a signature of dark matter production. Still no definitive discovery, but the search continues. And of course, underpinning all this is theoretical work, developing models, predicting signatures, guiding the experiments. And finally, none of this would be possible without massive computing power. Supercomputers are essential.
For analyzing all that data from telescopes.
Yes, handling the petabytes of data from surveys like Rubin is a huge challenge, but also for running incredibly complex simulations of the universe.
Simulating the Big Bang to today.
Basically, yeah. They model the behavior of billions of dark matter particles and gas particles over billions of years, governed by gravity and other physics. These simulations let us test theories. If we simulate a universe with a certain type of dark matter or dark energy, does it end up looking like the real universe we observe? They help us visualize the cosmic web, understand halo formation, and connect theory to observation. It's a vital piece of the puzzle.
So it really is this interplay between observation, experiment, theory, and computation, all working together on this immense puzzle.
It truly is. That ongoing tug of war happens in the research world, too.
It's just incredible, isn't it? The sheer scale of the unknowns, 95% of everything.
Yeah.
But also the scale of the human effort trying to understand it, the ingenuity, the persistence. It really speaks to that fundamental human drive to explore, to figure things out. It's the spirit of discovery in action. So let's try to wrap this up. We've journeyed through the dark side of the cosmos today. We've met dark matter, the invisible scaffolding, likely made of exotic particles, holding galaxies and clusters together through its gravity.
That cosmic cement.
Right. And we've encountered dark energy, the even more mysterious force, maybe an energy of space itself, pushing the universe apart at an accelerating rate.
The cosmic accelerator.
We heard about the first puzzling clues from Zwicky and Rubin decades ago, and how evidence from galaxy rotation, gravitational lensing like the bullet cluster, the cosmic microwave background, and the surprising supernova results built an undeniable case for these hidden components. And we've seen the incredible global effort underway to finally uncover their true nature. Giant telescopes mapping the heavens, sensitive detectors waiting deep underground, powerful colliders smashing particles, and supercomputers simulating cosmic evolution. It's clear we've unpacked a lot and found some amazing insights, but the universe, well, it still holds its cards very close to its chest on this one. So thinking about all this, what's the big takeaway for someone listening, maybe looking up at the sky tonight?
Well, here's a final thought to maybe noodle on. Consider this. What if that seemingly empty space all around us, the vacuum between the stars, the space you might think of as just nothing? What if that holds the key to the entire universe's ultimate fate? What if its properties, maybe that quantum foam we talked about, are dictating whether everything ends in ice or fire? We're only just beginning to probe the true nature of nothingness.
Wow.
And maybe reflect on the fact that everything we perceive as real, the stars, the galaxies, you, me, this planet, all of it is just this thin 5% frosting on a vast, dark, unknown cosmic cake. We are, in a very real sense, just a tiny component living within a universe overwhelmingly shaped and driven by forces we can't see and barely comprehend. What does that really imply about our place in the grand scheme of things? And what other profound, dark mysteries might still be out there, waiting just beyond the reach of our current understanding? The quest, thankfully, is far from over.